Hey, Mr. Dean here with another exciting video, this time talking about shifting, reflecting, and stretching graphs. Let's get into it. So the first type of graph you may run into is a constant graph. Pretty boring. Just go straight across, right? C is for constant. Maybe we can make it more exciting by making it negative. Well, not really. Or you could actually have it the most boring ever. Right across the x-axis at y, or f of x, equals 0. Well, we started to get things a little more exciting here, right around 7th or 8th grade, where you learned a little bit of algebra, and we could have a variable in there. And we could tweak that a little bit. We could move that graph up or down. We could change the slope of it slightly also. We could have it be a negative slope, move this way, or anything like that. And we transfer that all around back in algebra. Somewhere along the road, you learned about absolute value graphs. So that's the one that's shaped like a V. Oh, these aren't together, but the whole thing would have to go like this or up and down. We'll see that later. Little arrow symbols go with it, of course. And then we learned square roots. Now this is sort of the underdog of all of them. All right, and we want to be a little more particular than you maybe were in the past about how the scale works. If I go over 1 on my basic square root graph, I got to go up 1 because the square root of 1 is 1. The next time I land on an integer won't be until 4. The square root of 4 is 2. So I need to have that there, and there's my graph. So it can be a little bit more accurate than just throwing a curve on there. The next parent graph that we look at is anything to an even power. Usually x squared, but we can get x to the 4th in there, x to the 6th power. They all look like parabolas. They're even functions, so they're going to be symmetric around the line of symmetry, which is right down the middle of it. And another thing about the scale is that if you go over 1, of course, you go up 1. But in this case, you go over 2, you're going to go up 4. And if you go over as many as 3, you're going to be going up, well, you square that, for instance, you're going to go up as high as 9 there, way up here, and you get your classic parabola shape. Now all the negative x's that are over here, all those negative x values, of course they get squared and they become positive. All right, so that's why everything's kind of symmetric on that side too. Now our last of our 6 parent graphs in our toolbox are the cubic functions. X to the 5th, x to the 7th, any odd amount, right? Any odd exponent. Kind of gives you this sort of disco arm kind of thing with the green arms going up and down. One thing about that scale is that you have to go over 1 just to get to 1. But if you go over 2 and you cube that, you're all the way up at 8. So it gets big quick. The scale doesn't even do it justice. And of course, if you go over 3, cube 3, you get 3 times 3 times 3, you're already up at 27, which is probably on this scale all the way up here. So you get this. Now it is an odd function. So its symmetry is around, you kind of spin it around the x-axis, or y-axis, and you spin it around the x-axis. So it goes around both axes for some symmetry there. Those are our 6 functions, and we are going to mess around with them in terms of transformations. We're going to move them left, right, and everywhere. Here is sort of the breakdown of the different types of things you can do. The vertical stretch just makes it taller, or if this is like a fraction, it'll make it sort of fatter. If it's negative there, of course, it'll move everything over and around the x-axis, or flip it over, the up and down direction. Horizontal stretches, we don't worry too much about. That horizontal number, that stretch there, is often 1. And that kind of battles it out with the vertical stretch anyways. Vertical stretch is the up and down stretch. The horizontal stretch is the left and right stretch. And if you think of those like almost silly putty, stretching in the up and down direction, stretching in the outward direction, they kind of battle one another. So often at times that's just 1 to keep things simple. The horizontal shift, that's a big one. That moves things left and right. And last number there, D, it's often towards the end. It's the vertical shift, and that moves the whole graph up or down. All right, don't know why there's an extra parentheses in there. So there you go, A, B, C, and D. Let's get to it. Let's graph this function here, 2x squared plus 4. The parent graph, you want to identify that as x squared. So really in general, just a real general look at things, you're going to have some kind of parabola shape, right? And that's overall what this is going to look like. But we want to get a little more specific than just throwing that together. The A number is 2, right? So that's going to be the vertical stretch. So this is going to be stretched up twice as much. And the D number means the whole graph is going to start up at 4. So the whole graph, so that parabola shape is going to start at 4. And if I go over in the x direction, I'm going to be kind of specific with this. If I go over 1, well, normally when I square 1, I get up 1, but this time that multiplier is going to make everything, instead of going up 1, it's going to go up twice as much, to 2. So we're going to go 2 higher to right at 6. All right? The scale here is a little weird, but I went over 1, and I'm going to go up 2. And if I went over again, and I like to start back, if I go over 2 and start back at that vertex there at 4, if I start over, I go over 2, of course, square 2, I get 4, and then multiply that 4 by 2. Now I got to go up a total of 8, all the way up to there. All right, and I can just keep going with that pattern with 3 and 4, but we get the picture here. We know what a parabola looks like. So we're just going to take this side and make a nice parabola out of it. And we know that it is mirror image. So I'm just going to take the 2 points that I found and mirror image them over on the other side of the y. And we got a pretty good looking parabola. That will do, not bad. So stretched out in the vertical direction and moved up 4. All right, now we got a big mess of equations here. Let's get to it. Let's look at the red equation. Let's see here. The red equation here, that's definitely an x cubed looking graph. So I know that much. But there's something to it. It's not quite x cubed. Now this scale, everything's going by 1. The squares are 1. And if I go over 1, I have to go up 2. See that? I have to go up 2 before I get to that point there. And if I went over twice, I'd have to go up as far as 8, right to the edge of the graph. Actually, that's going to be even higher than that. So if I go over 1, let's see here, I go up 2. If I go up over 2, I'm higher than 8. In fact, that's not really that close. Turns out it would be 16. All right? If I went over 2, I would go over 16. If I went over just once, that's 2. That tells me the multiplier. It gives me a clue that there is a 2 in front of this. All right? Because if I change x by 1, right, 1 cubed is just going to get you 1. Normally I'd go over 1 and up 1, but this is going to go over 1 up 2. So that's where that kind of 2 is found from. So my red graph is 2x cubed. All right, next graph. Let's go with the blue graph. That blue graph looks like an absolute value to me. It looks positive because it's facing up. It looks like it was moved over to -2 and then down -4. So that, let me write it like that. That vertex right there is -2, -4. And it does look like the slope is up 1 over 1 the whole way through. So there's not going to be a multiplier besides 1. So I'm going to stick with, let's see here, absolute value is the parent graph. I need to move it over 2 spots to the left, so +2. I need to move it down 4 spots. And that's my graph, and I'm sticking to it. If I had more room, I would stick in y equals. Barely have enough room there. Really should have that. All right, yellow graph. I don't have a yellow marker. I'll have to go back with red, all right? The yellow graph is an absolute value graph, all right? That parent graph is absolute value. If you recognize that, it's upside down, kind of in disguise, and it's been moved over 3 spots and moved up 4 spots. So 3, 4 is its, for lack of a better word, call it a handle. I don't know. It's not really a vertex. That spot right there. So our yellow graph, parent graph is square root. Now let's see. We got to move it to the right. We said 3 spots, so that's a -3. We make sure that's under the hat of the square root. And then we're going to move it up 4, so we tag that on the end. And we have to move, if that's all we had, if that was our equation, well, this would look like that. All right? So we have to make sure 2 things. Number 1, as I go down 1, it looks like I go over 1. In fact, as I go down 2, I'm going to be going over 1, 2, 3, 4. And that tells us, just down 1 over 1, that that's very typical. and there's really just a 1 as a multiplier. But I need to flip it over. That 1 doesn't flip it over by itself. How do I flip it over sort of this imaginary horizontal axis? Throw in a negative right there. All right? So the square root function starts sort of its life. The basic square root function starts out like that. What I've done is I've moved it over 3 spots. I've moved it up 4 spots. And then I've flipped it over that axis. All right, that red dashed axis to get there. All right, the green graph is, oh yeah, that's classic. That is a parabola. It's moved over 5 spots. So it's going to be some sort of a x minus 5. We're going to square it, make sure we don't forget about that. It's upside down. We're going to throw in a negative sign. And then I'm just going to see if it was like maybe -2 or -3. And again, here's how you do that. Go over from the vertex 1 spot, and I see that I only go down 1 spot. Well, that tells me that that multiplier, if I squeeze this in here, again, I should have y equals, is -1. I won't write the 1. You know it's there. All right. So there is our 4 graphs. All the different ones transformed. It takes some time to get used to this, and it takes a lot of examples, and we'll do plenty of those in class. So thanks for sticking with us, and until next time, it's Mr. Dean saying, we're out of here in 11.5 minutes, a world record.